unknown finite value. Maybe it's 6, maybe it's 100, maybe it's a million. I don't know what it is, but it's finite. So the formulas apply to these three things. So now I apply them. What I'm going to get is I'm going to get a rational expression in n. There'll be no more i's, it'll all be in n. And then we're going to run the limit on that, and it's going to give us our answer. Okay? Roger, you seem skeptical.
Well, like, n is eventually going to go, n is a finite small number, right? So it's heading towards 0.
No, n is heading towards infinity.
Oh, okay, but it's like it's going to be on the top or on the bottom of the denominator.
You'll have both.
Would they cancel out?
A lot of them do.
Huh?
A lot of them do.
Oh, that's the reason it gives you a 5. Oh, okay, that makes sense. Because I was like,
is this one of those? If the bottom were larger, it could go to 0.
That's what I mean. Like,
oh, you're questioning, could you ever have more n's on top than bottom?
Yeah, it's like the thing is like if you end up having a scenario where n is on a like let's say bottom, you're gonna end up with a situation where it's gonna head off to infinity. So anything at the bottom is gonna be.
Yeah, you know what that would be? Oops, sorry. Read that screwdriver. But you have some asymptote here. What if I took the, try to find the area from 0 to 1? I'll try to find that area. Well, it keeps going up forever. So there's always more and more area still stuffed in there, right? More area. So if you try to apply this technique, to this situation, it could be you'll get a summation that when you put the limit on it, the degree of the top is higher than the degree of bottom, and it does go up to infinity. You're attempting to compute an infinite area. As opposed to over there, it's surely a finite area. It's trapped between two boundaries.
Yeah, so if we were to find
if you did the definite interval on this thing,
on a certain interval,
on 0 to 1 specifically, where it keeps going up forever, right? And never hits 0. It never connects to the y-axis. It's possible you would create an infinite area, and you won't be able to compute it. And it will be shown that one of these is infinitely large. The r's aren't going to be like that, and you won't have that until about 2 or something. And you won't do it by hand like this either. You'll do it using the fundamental theorem. You use antiderivatives, which we'll show next time. Right? But this is what we're stuck with right now, and so you shouldn't. Oh, how about that? And you should not be getting infinitely large areas. It should not happen. You did something wrong if that's the case. So now we're going to replace these symbols. So we have lim as n goes to infinity. So if this is n, what's 6 over n times n? 6. Guess what that 6 is? Can you tell? Where's that 6 coming from in my picture?
4 plus 2.
I think it's 1 plus 5, maybe. No, hold on.
How do you know?
What is this height here? It's 3, right? 2 squared minus 1 is 3. So this is a height of 3, but it has a width of, oh, that's long. Actually, I lied. Yeah, 2, width of 2. So that's the 6. That's where that's coming from. Okay? And now these other two are going to compute all this other junk going on up here underneath the smooth curve. That make sense? All right. So we got 6 plus, what's this one? I'm just going to write the symbols. It's 16 n plus 1 over 2, but there's an n squared on the bottom. All right, and the last one is 8, and then that formula, n plus 1, 2n plus 1 over 6, but it has an n cubed on the bottom, so 6n cubed. There. If we find this limit, we'll have the answer to the actual area underneath the curve. And what do you need to get that? I just replaced the circled red parts with their formula. Okay. And keep in mind these coefficients on the front. Right? So 16, right? 16 times n plus 1 over 2, there, and then n squares on the bottom. Just joining them all together. Now, here's the way to think about this now. You should note that for these rational expressions, the degree of top and bottom is the same for each one of them. Degree 0, degree 0, degree 2, degree 2, degree 3, degree 3, right? If you multiply this numerator out, you would have a third degree leading term, correct? You okay with that? This is going to cut this problem really short if you're just listen for a second. So, whenever you have the same degree top and bottom, and n, or the independent variable is heading towards infinity, that's a horizontal asymptote for that expression. But we also know it's a ratio of leading coefficients, right? Ratio of leading coefficients. Remember that rule?
Yep.
a rational expression? Let me get my fingers pointed.
Oh, okay, wait, one.
Yeah.
The cheese.
Got it? Alright. So.
Start to say cheese.
Sorry. So what is the leading coefficient on this expression? No, at the top. Just the top.
16.
What's the leading coefficient at the bottom?
2.
So therefore?
8.
Okay. So it's going to read 6 plus 8. What's the leading coefficient here? For this one. Be careful. Leading coefficient, 16, right? Leading coefficient up here is 16. How do you get a leading coefficient? You multiply all the leading terms together. So 8n times 2n is 16n cubed. That's the leading coefficient, 16. Divided by 6. There's your answer. 16 on 6 is what? 8/3, thank you. So we have 14 plus 8/3. 3 times 14 is 42. Plus 8 is 50. Our answer is 53rd. That's the exact area measured. Cow.
Exact area that's shaded.
That green round we give there, 50/3. Exactly.
Is that fraction like one of those fractions that goes on forever? Like
No,
1/3?
50/3 is no.
It's a set number?
Yeah, 50/3 is what do you mean? It's finite decimal expansion. All rational expressions are finite decimal expressions. It wouldn't matter. Even if it was √2, that would still be your answer.
Yeah, no, but I'm just saying. It's not the number that
It's not irrational. It's certainly rational. Right? There's this ratio, 50/3.
Can you like just briefly say how you got the 6/8 and the 66 from the end?
Since these are rational expressions, right?
Because they go
Polynomial or
to-
polynomial.
Yeah.
So and n is going towards infinity. So the answer is ratio of leading coefficients. But I want to make sure I'm careful about that though. So I look at what's the leading coefficient. Well, the leading term is 16n times the n.
Yeah.
So leading coefficient 16.
Oh, okay.
Leading coefficient 2, their ratio 8. Leading coefficient here, 8n times 2n is the leading term, right? Leading terms of each of them will be leading term of the product. So you have 16n cubed over 6n cubed, 16 over 6. Right?
Usually when you're doing these problems with curves, do they end up being a fraction? Because
Not always.
you find out a number.
It's gonna be a finite number, yeah.
Can I mean like the number 2 just by
Sure.
itself. That's amazing.
Yeah, I mean we just crush that problem.
I thought it would be like
This is the hardest thing that mankind ever came up with, right? Compute areas underneath arbitrary curves.
No, it's like
Man, there's just struggled for centuries, millennia.
I always thought it was like
And
pi.
Suddenly.
No way am I in-
How? I just did this like it was child's play.
No way am I answering that on a test.
But can't they
Oh,
find?
wait, here it's coming.
Right.
Practice the problem.
What's your
Lee, yeah.
Why do you say that 6 comes from the 2 times?
It's constant.
Was that whole thing one bump on the
The curve
Yeah,
itself, right, has no
Whole thing
impact
is
on
one
that block.
Yeah, that whole thing.
You know what I'm saying?
Gee.
So the curve has no impact on it, the function has no impact on it, and you expect it to be a constant in the expression. It's not, this thing doesn't change with the curve. You'll see, do more problems like you'll see. If you think about